Hi, and welcome back. This is going to be the final video for this week that introduces new material, with only a summary video to follow before you get stuck in and start working on some of these new ideas that we've introduced so far. Previously, we considered how, for a single model, we can use a distance metric or a loss function as a measure of model performance. In the coming weeks, we're going to consider many different types of modelling approaches. In supervised learning, as in life more generally, there's no single approach that will give you the best results in every scenario. Deciding which approach or model to use in a given setting can definitely be challenging, but it's one of the exciting parts of statistical learning that makes it an art as well as a science. In order to choose between potential models, we're going to have to explore the idea of model evaluation and comparison in much greater detail. This is something we'll return to again and again through the course, but this video will be our first serious treatment of the topic. In previous videos, we met the sum of squared errors as a measure of model fit, and commented on it having appealing mathematical properties. In this video, we'll focus on the mean squared error, which is a closely related measure, but gives an average rather than a total of the squared deviations between observed values and those predicted by our model. So looking at the form of these two measures, we can see that I've simplified notation slightly here. I've dropped the explicit dependence of our model function f on the parameters theta. Instead, I show that this is our fitted model by the addition of a hat above the f to show that this is an estimated function. And here I reserve the unadorned letter f for the true relationship between covariates and responses. We can choose to calculate the mean squared error on either our training or our test dataset. In either case, a smaller value is going to indicate to us that our modelled values are closer to the observed outcomes. Generally, we're going to be more interested in the mean squared error on the test set than on the training set. Can you think why that might be? So again, this is down to our desire for the model to be able to generalise. We want our fitted model to hold in new settings. For example, we don't really care how well we can predict the voter share in the last election after it's already happened. What we're really interested in is predicting voter share in the next election instead. Even in a scientific context, where the primary goal is to understand the function f itself, rather than directly to make predictions, this idea holds true. Ideally, in the previous example that we considered, for an acceleration model from the previous lecture, we'd like that model to hold if we were to drop the object and measure its fall again and again and again. We need our models to work with new data. As we saw in the previous lecture, different models have different amounts of flexibility in how well they can match up with the test data. The flexibility of a model in this way can be measured in terms of its degrees of freedom. The degrees of freedom of a model is effectively the number of independent parameters that we can select the values of when we're fitting that model. For more complicated models where the parameters aren't chosen explicitly or are highly dependent on one another, the number of degrees of freedom is some approximation of this parameter count. The more parameters we can set, or the greater our degrees of freedom, the more closely our model can match the training data. This means that our training mean squared error will always decrease, or at least not increase, when we make our model more flexible. But this gives us no guarantee that this same effect will transfer into our training mean squared error. And remember, this is what we're really interested in going beyond our training sample. What we might be doing is just better modelling the noise that is on top of the signal in our data, and it's this signal where our interest truly lies. In these graphs, we can see how, schematically, the test and training errors change with model complexity. A more flexible model is never going to increase the training error, but only reduces the test error up to a certain point, after which we begin to overfit with our model, and additional degrees of freedom are going to impede our ability to generalise to new data points. We can use this idea to find the best model from within a collection of models, by splitting our data into a training and a test set. The training data can be used to pick up the best parameter values for each model by minimising the training mean squared error, and then the models can be compared using the resulting test mean squared errors of the optimised models. There is, of course, a lot more that could also be done here, and plenty of care needs to be taken when selecting exactly what goes into the training and test datasets. For those of you crying out to the screen right now about validation sets, the jackknife and data leakage, don't worry, we will be revisiting this in the future. So let's consider now the expected squared error for a single new observation y0, which we haven't observed yet, and which has covariate values, which we'll call x0. This quantity is like the mean squared error, but over all possible new observations with the given covariate values. By now you should be starting to become familiar with the idea that in a supervised learning setting, we consider the value of y as some deterministic function f of its corresponding covariance, with some additional stochastic noise, which we're calling here epsilon, on top. In the lab this week, you're going to see that the expected squared error on a new observation can be decomposed into three quantities: the variance of the fitted model, the squared bias of the fitted model, and the variance of the error terms. The first two terms here are the only ones to rely on our choice of model, and notice that these are both non-negative. This means that the last term, the variance of the error terms, is an irreducible error. No matter how good our model is, we can never get our expected squared test error below this value. The other two terms, on the other hand, are things that we can control based on our modelling approach. The variance of our fitted model quantifies by how much our predictions would change had we used another test dataset, with the same covariate values but different stochastic noise. A small variance in our model means that our resulting model fit is stable to changes in the training data, while a large variance means that our model is highly sensitive to even small changes in the training dataset. The other term here, the bias of our fitted model, is a measure of the expected discrepancy between model predictions and true values, and as such can either be positive or negative. Since we're considering the squared bias here, this is going to be non-negative, where smaller values correspond to better predictions. The squared bias gives us a way to quantify the amount of richness that we've lost by reducing the complicated and interconnected real world into a model that we can actually work with. To select a model with the lowest possible mean squared error overall on new observations, what we would really like is a model with both low bias and low variance, seeing as we can't do anything about that irreducible error. This is why the trade-off part of the bias-variance trade-off comes in. Generally speaking, as model complexity increases, the bias will also decrease because we're missing less of the signal from our data. However, what this means is that as the model complexity increases, we're also including more of the noise component of the data within our fitted model, which is going to increase its variance. This combines to mean that the model variance increases with degrees of freedom, while squared bias decreases with degrees of freedom. Picking a model that generalises well is going to require a balancing of these priorities to result in the lowest possible expected value for the total squared test error. The level of flexibility that is required in any particular model is going to depend on the complexity of the signal in the data that is being modelled, and the ability to discern this signal from the noise that obscures it. I'd like to round off this final video by pointing out that in practice, the true function f is of course going to be unknown. If it were known, we wouldn't need to be going to all of this effort to estimate it in the first place. Importantly, without knowing f, we can't decompose our mean squared errors into bias, variance, and irreducible error terms. But that doesn't mean that thinking along the lines of these terms isn't still a helpful thing to do. Indeed, we should be keeping this decomposition at the forefront of our minds as we progress through this course. Keep asking yourself whether we're making real gains by using progressively more complex modelling approaches, or if really we're just better describing the noise within our data. We focus very much on the L2 loss within this video, but the core ideas here extend across all loss functions. When choosing an appropriate level of model complexity, we have to balance between our model's fidelity to the true data generating process and its stability over realizations of our data. We've seen in this video how training and test errors change with model complexity, and how we can use this to select the most appropriate model. In the labs and live sessions later this week, you're going to be exploring all of these ideas further. Next week, we'll begin our exploration of supervised learning models in earnest. We're going to begin with our beloved linear model, which forms the basis for many other models, which we'll meet later in the course, and which, despite its simplicity, can be highly effective in many settings. I look forward to seeing you in the next week, and thank you very much for your attention.